Okay, this is going to be the third video from section 2.3, and it is covering what I like to call the replacement theorem. Okay, this theorem is in your ebook on page 98 in a little box. It describes it, it says it in notation. However, they don't use the title replacement theorem, they don't call it that. I got that title from my Math 26 book, which is a different version of calculus that some Sac State students take. But I really like that name, replacement theorem. A theorem, first of all, in math is just a claim that's been proven. Okay, so something that you can take for granted. We're not going to be proving it. It's pretty intuitive graphically when we get to that point. But anyway, it's not called that, but I'm going to use that phrase a lot. Okay, and I posted some class notes about limits, and I described it in those terms. All right, so let me get rid of that page number, but again, that's page 98. So first of all, we looked at this example in the previous video. This function g is what we would call a rational function, and the key word within the word rational is the word ratio. Ratio sort of just means a quotient or something over something else, right? A fraction. And so a rational function is specifically a ratio of two polynomials. Okay, so in the previous video, I kind of talked my way through the definition of a polynomial. So that's what I've got up top, that's what I've got on the bottom. So we can use direct substitution. We can try it if the function exists there. And if it exists, that means we'll get a real number as the output, and then that would be our limit. And as I did in the previous video, and I'll typically do anyways, let's try direct substitution first and see what happens. Okay, so I just erased the question mark. I'm asking, what is this limit? Let's try direct substitution. Okay, so direct substitution, I'm going to let x be 2. I'll do it pretty quickly. I did this in the previous video. 2 squared is 4 minus 4 is going to give me a 0. 2 minus 2 is going to give me a 0 on the bottom. Okay. This expression, 0 over 0, that's not a number, right? It doesn't exist. It's like saying Santa Claus over Easter Bunny, right? No, that's a bad example. But it's more like Santa Claus. It doesn't exist, right? And kind of whatever. I'm sorry if I'm spoiling your Christmas. Doesn't exist. It's definitely not equal to 0, and this doesn't tell us what our limit is. It doesn't really guarantee that our limit exists or not, but it begs further investigation, okay? So when we get 0 over 0, one thing we're going to see a lot is that's going to indicate that there might be a hole, okay? If we get a non-zero over 0, pretty much always means, and that's again for a particular x value, so you let x go to some value and you end up evaluating it and you get non-zero over 0, that's pretty much always going to indicate that that graph has a vertical asymptote, which means it's blowing up either towards infinity or negative infinity. Okay, so that's something to investigate. 0 over 0 means there might be a hole. There are cases where you might still have an asymptote, so we'll discuss that in time. But let's decide how we know if we have a hole, okay? So let's look at this function again. Let me do this. So the limit, I can do this while using limit notation. So the limit as x approaches 2 of g of x is the same thing as the limit as x approaches 2 of the way I've got that written, x squared minus 4 over x minus 2, okay? So, nothing strange happened there, right? G of x is the same as that. They're different names for one another, so we haven't done anything there. Let's factor here the top and the bottom, right? Let's factor the top. The bottom here is a linear term, can't factor. But let's factor the top. And I'm still writing limit here every time. I mentioned in the previous videos that after direct substitution, we stop writing the little limit phrase. Up until we do that, we keep writing it, okay? That's important to indicate what's going on. So I can't say this is just equal to x plus 2, x minus 2 over x minus 2. That's not true, because this is a limit, and then that's just a ratio or quantity, a new function, really. So until you actually send x to 2, you've got to keep writing that, okay? And again, I'll emphasize that we're not doing a ton of paperwork here, but we will sometimes, and that's what I'm looking for. It's really just accuracy of notation, okay? A lot of students leave. I run into 2 examples. Some students write limit every time, even after direct substitution, which is sort of overkill. Others just never write it and then just put it at the end, which is sort of a little bit, or not enough work. Anyway, what do we notice here? So this is something subtle that's going to happen. We're going to replace this function with a more well-behaved one. The original function here, which this is a reworked version of my function g, is not defined when x equals 2, right? That's a particular function that's not defined when x equals 2. 2 is not in the domain. So a function is defined by the rule and also its domain. So this function g, 2 is not in the domain of the function. What you probably see, though, here, and what you might expect me to do here is sort of cancel out those x minus 2 terms, right? I'm using green there. Let's see if we can see that, but canceling out those terms. Pretty common idea, right? Okay, when we do that, what we've got left now is this piece is still here, right? That x plus 2 in my numerator is still up there. And in the bottom, you could argue I've kind of got a 1, right? Sort of a hidden 1 is still there, okay? And so what I'm doing now is equal to, trying to color code this, this is equal to the limit as x approaches 2 of sort of this simplified version of g, all right, which is just defined as this function, x plus 2. So what we're doing now is the limit as x approaches 2 of the new function x plus 2, okay? I could call this I could explicitly title this guy, right? I could say down here, let f of x, since that function up there is called g, I'll call it something else. Let f of x equal this guy, right? You don't really have to do that. But I'm doing my best to indicate that what we're really dealing with is a new function here. They're going to share all function values, though. If you were to graph these both on Desmos, so if you first graph this, you're going to notice what it looks like in a certain graph, and it's going to have a hole in it, though, when x is 2. It's going to have a hole, right? But other than that, and you can see the shape, I'll probably mention that in a moment, see the shape of that graph. You might want to pause the video now and do that, just as a little investigation. Graph that thing, see what it looks like, and notice that it has a hole, though, when x equals 2. But notice where the hole lives and sort of what the left and right hand limits are approaching, right? As we come from the left and right, what are we getting towards? Okay, so that's cool. At this point, so let me mention here, this equal sign, when I went from this complicated function not defined when x is 2, and replaced it now with this simple linear function where plugging 2 now in is not a problem, right? This is just a polynomial, the equation of a line, and so the domain of this new function f, is all real numbers. So that's why I replaced, that's where the replacement comes from. I replaced this complicated function that has a hole with a nice line, just a straight line that has no hole. And so, again, most teachers probably won't ask you to do this. You won't see it in the textbook, but I ask students to indicate, just so I know that they know what they're doing, or I know that you know what you're doing, indicate that we just used the replacement theorem there, all right? And the replacement theorem is great, usually, unless you have another problem, right? If we were still had other issues, other terms giving us zeros in the denominator, we might have to do something else. But at this point, typically, the next step is now just do direct substitution, right? Direct substitution. So that means drop the limit notation, let x become 2, right? So I'm going to have 2. This 2 is jumping right there. Then I've got this plus 2. I'm writing here in purple. That was just part of the function, right? This new function just says take the input, add 2. 2 plus 2 is 4. Boom, we've got our limit. Okay? That's really interesting. There's not really a way of verifying this now algebraically. In other words, if you look back to the original function, other than trusting this theorem, let me say that. But if you just look back to the original function, there's no way you could really tell that the graph of this will have a hole at the point when x was 2 and then this height 4, right? So the original graph has a hole at the point 2, 4. When you then, as a second step, graph this function, f, it's going to look exactly the same as g did, except now the hole is filled in, right? So what we did here algebraically by using the factors, canceling them, we're sort of fixing the problem. We're kind of replacing it with a filled in. We sort of patch that hole, right? And then now we can use direct substitution to figure out exactly what it is. Okay, so I can't emphasize enough that I don't know how to say this. I can't suggest enough or emphasize enough how important it is to graph these functions and kind of see that replacement theorem happening. The book has some nice versions of it as well. So another example on page 98. So same page where this replacement theorem is described. But yeah, so that's pretty good. Okay. A couple of students asked me some ask your teacher messages regarding this thing. So I described this whole process of what to do. And then as a follow-up, I said what I just said to you folks now in the video is check it graphically too, right? You could, I guess, avoid the whole algebraic thing, right? Avoid this notation, avoid writing all this out or doing these steps by just consulting the graph, right? If the first thing you did was say, let me just plot this graph and see what it looks like is happening near the value of x of 2, right? You'll see a hole, so you know the function doesn't exist. But again, if you see a graph that looks like this, for some, let's say, particular a value, make sure I'm not kind of in the glare right there. If you see a function like this, and so for some particular a value, you see a graph that looks like that, right? Or it could be a curve, then I see a little open dot right there, so the function probably doesn't exist. But whatever the height of that dot is, that's the limit, because as I approach on the left, I'm climbing up to that height, and as I approach on the right, I'm, in this case, descending towards that height. So as we approach a, the function is approaching this value right there. All right, so kind of cool. And let me end that right there. Yeah.